This paper was presented at the JCT Traffic Signal Symposium 2025. Video coverage of this paper is provided by Highways News and sponsored by Mobius Networks, AGD, Smart Micro UK, TRL Software, Traffic Group Signals, AD Electronics, and 4-Way Consulting.
Thank you very much, and hello everybody. I shall go on to this one. Joel, I left Leeds ITS in 1976 and went to work for West Yorkshire County Council. And the first thing I worked on was a new tram system for Leeds. So good luck. But I'm going back nearly 100 years. Well, in fact, I'm going back a bit further than 100 years. Two people have already mentioned this, which is a bit annoying. 1868, the first traffic signal, really. This was the semaphore signal installed on Parliament Square in Westminster. But this gentleman is, if I remind myself of his name, John Peake Knight, who's the first traffic engineer, I would contend. He was the one who actually installed this traffic signal. It included, up there, red and green gas lamps for use at night. One of those exploded and injured the policeman who was operating it down there, and the thing was taken out and the experiment wasn't continued. But after the First World War, motor traffic was coming to dominate and junctions needed controlling. This is Town Hall Square in Sheffield. And you can see, oh, sorry, pressed the wrong button again. There is a policeman who's doing point duty. That's a close-up of the little box he stood in. This is what was repeated over the whole of the Western world, really, particularly in America. There were 6,000 traffic officers controlling junctions in New York. Great pressure to develop some automatic traffic signaling. All kinds of fancy things were tried, but it evolved to become the three lights that we are used to nowadays. But these were all fixed time installations which were just based on advertising sign kind of technology. It took the UK quite a long time to actually adopt this. In 1926, they tried a thing in Piccadilly, a junction in Piccadilly with light signals, but they were operated by a policeman pressing buttons in a little box. But in 1927, the first automatic traffic signals in the UK were Princes Square in Wolverhampton, and this is it. There's still the policeman controlling traffic, but hanging over his head is the traffic signal, the first automatic traffic signal, a fixed time signal, installed in 1927 in Wolverhampton. It was a success, and in 1928, they actually moved that down to a post in the middle, which actually stayed until the 1960s. But that was the first automatic traffic signal, and the pressure to produce a vehicle-actuated traffic signal was really quite intense. By 1930, there were 135 fixed-time signal installations across the country and a lot more in London itself. That in 1929, the MOT, the Ministry of Transport, had introduced advice as to how to install traffic signals, but they were still all fixed time. 1932, this is the junction of Cornhill and Bishopsgate in London, and this was the first vehicle-actuated installation. It was an electromatic system. Electromatic became various other things, and I think they became GEC, who are now, then became Peak, and then became Intec, and now are part of Swalco, I believe. But this gentleman, we don't have to use top hats now when we're switching signals on. but this is the Lord Mayor of London, Sir Maurice Jenks, switching the first vehicle-actuated traffic signal in Europe on in 1932. The electromatic system used two spring steel plates separated by about 1/8 of an inch, which were pressed together by vehicle tyres, and that's how the detection was made. There was a rival system, which was the Autoflex system, and that used pneumatic tubes. You could make the electromatic spring steel plate systems directional. The Autoflex pneumatic tube ones were 2 tubes, so you could make them directional really straightforwardly. But both of them could also measure vehicle speed by the duration of time that either going from one to the other or for the length of time that the plates were compressed. And they did make use of that information in the control systems that were put in. The detectors had to cope with tramways, so short one and a long one. Trams were detected usually with a contactor on the trolley wire, and they were all taken into account in the operation. This is before the Second World War, this is in the 1930s. That's an electromatic signal controller. You've got timing dials here. Behind there you've got a cam shaft with lots of different cams on, operating contactors at the top here. So that was changing the configuration as the cycle went through. And this is an early traffic signal engineer installing one of those in Piccadilly in 1936, helped obviously by this policeman who was looking on, not necessarily terribly approvingly. I hope that there was no power being applied to that controller, because this is the circuit that was used for timing. And actually, the difference between the plus and minus was 412 volts. That charged up this condenser, capacitor nowadays, through a variable resistor which adjusted the timing. When that reached the striking level of that neon tube, that passed current through the relay when that detector was operated. But if you had a conflicting phase which had that detector on it, that would short out the condenser, which would then have to charge again. That was the way that timing was implemented in the electromatic system, and this was prone to quite a lot of error, I suspect. We were also just starting to get the nomenclature right. This was one of the things that people commented on in papers to the Institution of Electrical Engineers, was that people didn't actually understand what other people were talking about because they used different terms. But phase A and phase B, that had become established. I think these are what we would call stages nowadays, but they call them cycle parts. Minimum green, maximum was established. And then we had this speed timing period, which is basically where we would think about applying extensions. So that's how they describe the operation cycle of a two-phase, two-part cycle, two-stage vehicle-actuated controller. They also were aware of that it's a good idea to link signals together. So this is a hypothetical set of controllers, but speed distance diagrams drawn so that you could get progressions through. This is a 15-mile-an-hour one. And from that you could work out when you want each green to appear along the road. And the way that you would implement that was with a master controller with all these connections to be coming from the relevant time and distance diagram. And then it's pulses which were sent over telephone circuits to the local controllers. These were implemented really quite widely, Amsterdam, Berlin, and Chicago actually had the whole of their city traffic signals, which were all operated from a central location. So this was UTC installed in the 1930s. They had automatic switchover on failure between master controllers and remote alarm indication to the police and to the maintenance. Again, things which were implemented electromechanically in the 1930s. They did before and afters. This is a main road journeys through the new Oxford Street system, which was a fully vehicle actuated, flexible, progressive system. And interestingly, Mr. Tyack, who was the guy who wrote the paper from which I nicked this slide, in 1936 he did this one in an Austin 10. In 1937 he did it in a Morris Minor, so perhaps he got himself a new car. But clearly his boss, Mr. J. Paston Green, did it in his Lagonda. But there were a lot of linked systems. So this is a map of West London in 1936, showing all the linked traffic signal systems that were installed in West London. And you think that this was less than 10 years after the first fixed time signal was actually installed in Wolverhampton. And I'm just coming up to 10 minutes. That's a pedestrian detector, light-operated pedestrian detector. And you've heard of Belisha beacons. That's Leslie Hall Belisha, who was the Minister of Transport, and here he is inaugurating a light beam pedestrian detector crossing in Croydon. I think that was in 1934. And that's me finished, and I'll pass on to Howard. I think the red light has only just come on, so I'm feeling quite good.
Okay, so we're now going to come right forward. We're going through from the 1950s through to the 1990s, and I'll get a bit more technical as we go on. So who's ever seen one of these? This is a Electromatic Type 54. Not quite sure if it was cam driven. I don't think it was cam driven. Certainly lots of relays. If you have a look, lots of banks of relays here, tons of wiring. And there's some dials at the top here which are set timings. I'm going a bit too fast, but timings. A lot of wiring in there. This was probably not driven by a camshaft, as I said, but I've actually been present in one of these, and there's a lot of clicking that goes on with all those relays. So coming forward another 10 years, this is the Plessey 70. Plessey actually took over ATE. Plessey 70 actually looks very similar to the 70R in the 90s, so I'm not absolutely certain, but there are timing dials on here. There are sort of wired and soldered connections, and again, an awful lot of wiring. Moving on a bit further, and around the same time, is the GC25, very widespread, very widely used controller. Some described it as the Ford Cortina of signal controllers, but I suppose that might be a bit lost on some of you here. You can always phone a friend if you don't really understand. And to change the timings on it, there's a lot of information here, but you just had to remember you had to take out some plugs and some screws, and you had to make sure you didn't lose them when you're changing the timings on the signal controller. Coming forward, the first microprocessor controller I came across was the Plessey 200. This is a rack-mounted controller. It's very popular in the mid to late 1980s. And then followed on from that, the Siemens T400, also a rack-mounted controller. You can see in the racks here, and there's space for OTUs and various things like that. One of the interesting things about that, because of the rack mounting, is it was possible to mount it in a different controller case, which they called a cuckoo. So as a cuckoo, I don't know if do they still exist, cuckoo controllers? Okay. So there were various cuckoo options. This is a Franti Mark I. This is the small version. Ferranti was a controller supplier coming from a computing background and a military as well. They came into traffic through UTC systems initially, and this is their smaller 8-phase controller, also a rack-mounted controller. But then there was this, which is rather a beast, larger controller, up to 32 phases, and any number of parallel stage streams, which I'm going to be talking about in a moment. But that was really quite unimaginable a few years earlier. And then in the 1990s, which is as far as I'm going to go for now, this is a Microsense controller. Microsense came into the market, into traffic control market in 1990s. And it was this control. We actually helped develop some LRT software, tramway control. And on this, it's not rack mounted. The processor and the various control circuits are actually at the back, and then they've got the wiring all the way around. Right, just a brief look at the market, actually, since Peter talked about some of this, but you can see initially in the 1980s, the first controllers, microprocessor controllers on the market were Plessey, Ferranti, and GEC. GEC had come from Elliott, Plessey had come from ATE, which is automatic telephone exchange company, I think. And you can see that later in the 90s, Peak were quite active in buying out other companies to dictate the share of the market. And I think some people in the audience know a bit about that, Alistair. So there was, and obviously this is only going through to the 1990s, but we all know that the names of companies have changed with Peak and Imtech and what is it now? Moving forwards. So it's certainly the names changes, the controllers don't always change that much. But the thing that I really want to talk about is a bit more technical, is about the introduction of microprocessor signal controllers, particularly in the 1980s. And these are going to be some of the key issues I'm going to be looking at rather quickly. Most of the requirements were defined in a new DFT specification, MC0141, which came about in the early 1980s. I'm not sure exactly when. And it was a result of interaction with user groups with the Department of Transport. But it's very significantly influenced the specification of microprocessor controllers. So one of the first things is the controller specification methods. Probably one of the biggest, most important things was the separation of firmware, which is like the controller main software, from the site configuration. And I'm sure you're all aware now that's absolutely fundamental to the way that signal controllers operate. And obviously the hardware as well. Whereas previously, controllers were very much wired in, sometimes on site, sometimes in the factory. It was very difficult to actually change them. And of course, the introduction of handset rather than various other ways of introducing timers made it so much easier to deal with, particularly on testing and commissioning. On the integration of facilities, I think one sometimes forgets that on solid state control, almost any additional control mode required additional equipment. So that, for instance, UTC required a special modification and some equipment, and cableless linking had a completely separate rack, a cableless linking unit. Some of the other things also require additional hardware wiring. But on microprocessor controllers, most of these things were either integrated or they were integrated a bit later on. And things like Mover certainly started out as a separate unit. Is it now integrated in software? I think on some controllers it's integrated on software. I'm a bit out of touch, 5 years. Stages and phases. Peter hinted at this. Whenever you look at documentation of really early signal controllers or signal control, they use the term phases, but they actually mean stages in terms of what we would refer to them now. But the introduction of phase control within stages was absolutely fundamental to the way that microprocessors worked. And this basically meant that lots of phase-based timings could be introduced, both intergreens and phase delays and various other things. Dummy phases was a new terminology, but it's predominantly a software tool to constrain operation of different movements rather than actual timings. The introduction of max timers on phases is quite interesting because sometimes you've got some effects that are not quite anticipated. If you have different phases on the same stage and they have different timings, then I put out a challenge to people as what the time actually runs when you have extensions on one of the phases, which isn't the longer max time. Stage change mechanisms, this is really quite different because previously controller suppliers used to more or less deal with the what we would call the configuration of the controller, how the junction operated, and designers were rarely involved. With microcontrollers, the signal designer became much more involved, and the site configuration was a place obviously for doing that. But we had to learn this term Boolean conditions, and that was really quite a sort of fundamental change. One of the other things that was introduced, at least initially on Ferranti controllers and then later on other controllers, was ripple stage changes. I think some of you will have come across those. I don't know how widely used they are. I just want to give one example of that because in some cases they can make very significant changes, in other situations very little. So here's a junction. It's quite an unusual junction, but it's actually very similar, as I remember it anyway, to a junction that we had in Sheffield. And the stages almost slide into each other, or they can do in the different sequence. If you look at the different stages here, and I'll just put up a stage change diagram. And the red arrows are where the stage changes occur. And you can see under a ripple change arrangement, stage changes can take place before the previous stage change is completed. So that in this instance, which is quite unusual, I think it is quite extreme, you can have a signal cycle of perhaps, this is, I think, 36 seconds, where if you did it conventionally through standard stage changes, waiting for the intergreen and min for every phase that was being introduced to expire before you make the next stage change, you're running to a cycle time of 65 seconds, which is a really different sort of operation. And particularly when you talk about pedestrian facilities, actually, I'll just go back there. When you're looking at the pedestrian facilities, this makes it actually much more flexible to operate. So it's something that's worth bearing in mind. The only thing about it is, unfortunately, UTC doesn't really like it because some of these changes means you can go through 3 stages or the start of 3 stages in perhaps only about 3 or 4 seconds. So in practice, we had to have sort of merge replies for different stages to be able to come up with something that UTC could understand. Parallel stage streams was another innovation of microprocessor controllers. It didn't exist on solid state controllers. You needed multiple controllers for multiple nodes or anything like that. Obviously, this made it possible to introduce multiple complex signal junctions and signalized roundabouts. Also became much more viable because they're all constrained by the same controller, and synchronization issues between the different nodes of the junction really more or less disappeared. Also, in terms of the actual linking of the streams, you could either do this by timing on a pure timing base, it depends on very site specific, or you could do cross-linking the streams, particularly in fixed time and VA mode, or that even in UTC and CLF mode, where we've certainly had some junctions that I can recall where we had cross-linking even in CLF, which was quite complex to actually work out at times. I've lost my mouse. Where's my mouse? It's gone over there. Right, okay. Right, timetable and timings. Interestingly, signal controllers previously didn't have time clocks on them. So there were cases where people actually introduced electromechanical time clock, which is pretty much like you would have had on a central heating system, with the little lugs that you change at different times. But it was fundamental on microprocessor controllers to include a time clock for all sorts of functionality, for changes of timing sets, changing of modes. And the changing of modes was a new function in itself, really. Changing of VA times as well as changing of CLF times all became possible. So that was a really important change. And the fact that that's all integrated was very significant. The other thing is itself, timing accuracy on solid state controls was really poor. I think that was often influenced by the fact that the timings was based on mains frequency. And when mains frequency drifted, you used to get quite a lot of drift in time. And different junctions could actually drift out of sync if they were synchronized. So when micros came along, the accuracy was much higher, and it was possible to link by UTC, to synchronize by UTC, but it was really much less significant. There are examples I know of people in the industry who used to go around with a handheld stopwatch to time sync different junctions using their cableless linking unit, which was quite a task in itself. So that was even before quartz watches. Oh, one thing about that is interesting, that when remote monitoring first came out, which was primarily for solid state controllers, that was fine because you could tell about if there were particular problems. But when people started adding remote monitoring onto microprocessor controllers, you actually came up against an issue of which was more accurate, the microprocessor on the remote monitoring unit or the microprocessor and the controller. So that, you almost need a three-way system to actually work out whether that's a reasonable thing to do. Fault monitoring and safety is probably the last area that I look at. There was very little on fault monitoring and safety on solid-state controllers. Generally, the signals obviously were prevented from driving conflicting greens, but if there was any sort of electrical fault on the system, you could get green conflicts arise, normally with a green and an amber, or green and some other aspect, possibly through a short out on a pole or a cable somewhere. The fundamental within the microprocessor spec was about various means of preventing green conflicts, and these are, you'd be familiar with correspondence, equivalence, and checking, and also constant validation in a cycle to make sure that green conflicts aren't taking place. And then later on, lamp monitoring itself was integrated into many controllers, and detector and fault monitoring were also very detailed. One of the things about this is that with a detailed timetable, it became possible to get detailed fault information as to when faults were arising and exactly what the nature of those faults were. So that's a brief review, quick flick through of that. Hope you've given a brief understanding of some of the changes and why they were so significant and why they've led on to the sort of changes which should now become much more possible and more modern controllers. So at that point, I'm going to close. I'll just add one quick note that I'm doing a bit of research into old signal control and old signal controllers. And if anybody's got any useful information or actually pieces of equipment, I'm quite interested to hear about them.
Okay.
Thank you.
Howard, please, round of applause, please. Thank you. Well, I certainly feel like I've learnt a lot from the two of you. Are you happy to take a couple of questions? You were like, I don't know if you were sloping off. Are you both here this evening for the gala dinner? Okay, well, obviously, I think there'll be a lot of questions, people trying to tap into your knowledge, and probably a few of the things that you've presented have triggered memories and a lot of thoughts and things.
Perhaps more of them from Howard than from me, I think.
Well, yeah.
Hopefully.
Yeah.
Well, Peter, I think that my one takeaway from yours is that we should all still wear top hats, but maybe not. So, if we could have a couple of questions, that would be great. If not, we could wait until you see these two guys in the bar. I thought you got away with it then.
We're not going to let him off.
Mike, is there an award for the nerdiest question of the day? Because
Sure.
I'm about to make a bid for it. Gentlemen, you alluded to the fact that you put some of the first tram control and signalling into Sheffield a little while ago. Can I ask, did you ever do forward points indicators as part of the signalling system? The reason for the question is that there is a Topaz standard for tram signals, and we're being asked about forward points indicators. I'd like to talk to you later, basically.
Interestingly, point indicators came under what was the railway inspectorate control in terms of specification, and there was an argument as to whether, if a tram's turning left, whether you should merge the traffic signal to show that it's green from a point of view of traffic conflict, as well as from a point of view of tram equipment, point equipment, and decided not to, because they didn't really want to confuse what the issue was in terms of a fault if it didn't arise. So you can get situations where you get a green tram signal and a red or a bar point indicates, but at least people know what the issue is.
Thank you. Was that nerdy enough, Mike?
It was pretty good for this time of day. Pretty good. Do we have any other questions, or are you going to save them all for later? Are you both here tomorrow as well?
Yeah.
Yep.
I would like to invite you both to the Swarco stand. We have our new PTC3 controller. The P stands for peak.
Right.
So, yeah, I think...
I think I ought to point out that Howard is actually wearing a
Authentic.
GEC tie. So he's prepared to take bids for
Yeah,
it.
I'm going to put it up for auction later.
Great. Another round of applause, please. Thank you.